Chapter 68, Comets and Their Spectra Besides the Planets, which already cold or in process of cooling. Derive their light from the heat of the moon, give promise of the good work we may expect from his use of the noble instrument now in his hand. All traveling nearly in one plane among the fixed stars in regular progress from west to east, there appear from time to time certain ether-wandering stars of peculiar aspect, which, from their rapid change of form and size, their fantastic contour, and their brilliant light usually excite the greatest attention. These remarkable visitors are comets, and though their laws of motion have been well ascertained, yet their physical constitution has presented greater difficulties to astronomers than even that of the nebulae. When they first become visible, their motion is evidently round the sun, but frequently in orbits of such great elongation as hardly to be called elliptical, traveling, besides, in all possible planes and directions, sometimes like the planets from west to east, sometimes in the reverse way from east to west. Several of these extraordinary objects move H-closed orbits around the sun with a regular period of revolution. Others come quite unexpectedly from the regions of space into our system and retreat again to be seen no more. The periodic comets are as follows: period, distance from the sun, comet, perihelion, aphelion, years, miles, Encke's 289 millions, 350 millions. Winnicke's, Brorson's, Fiver, Biela's, 678. Faye's, Halley's. While these comets have but a short period, there are others, such as the comets of 1858, 1811, and 1844. The calculated periods of which amount respectively to 2100, 30, and 100 years. Differences of quite a proportionate magnitude are observable in relation to the points of nearest approach to and greatest distance from the sun. Encke's comet is 12 times nearer the sun at its perihelion than at its aphelion. Some of them, with an orbit extending beyond Jupiter, approach so close to the sun as almost to graze the surface. Newton estimated that the comet of 1680 came so Donati's comet on the 2nd of July, 1858, near to the sun that its temperature must have exceeded by 2,000 times that of melted iron. At its nearest approach, it was removed from the sun by only a sixth of his diameter. The comet of 1843 also was so near the sun at its perihelion as to be seen in broad daylight. Most comets exhibit a planetary disk, more or less bright, which is called the nucleus, and this is surrounded by a fainter cloudy or nebulous envelope, the coma. The nucleus and coma form the head of the comet. In almost all comets visible to the naked eye, there streams out from the head a fan of light, the tail consisting of one or more luminous streaks, which vary in width and length, are sometimes straight, sometimes curved, but almost always turned away from the sun, forming the prolongation of a straight line connecting the sun and the comet, while telescopic comets are usually without a tail, which causes them to assume the appearance of a more or less irregularly shaped nebula possessing a nucleus, an example of which is given in Donati's comet, figure 213, as it appeared when first seen on the 2nd of June. 1858, the comet of July 1861 exhibited two tails, figure 208, and the comet of 1844 had even 6 July, comet on the 3rd of July, 1861. Comets are transparent in every part and cause no refraction in the light of the stars seen through them. Bessel saw a fixed star through Halley's comet and Struve one through Biela's comet. When distant only a few seconds from the center of the nucleus which passed over the star, in both instances, without either rendering it invisible or even perceptibly fainter. From accurate measures taken at the time and the calculated motion of the comet, it was evident that the position of the star had not been changed by any refraction of the light. Similar observations were made with respect to Donati's comet of 1858, figure 209, and the comet of July 1861, figure 210. Close to the head of the former, where the tail at its commencement was a boate 540 miles in thickness, Arcturus was seen to shine with undiminished brightness. While in both comets a number of fixed stars appeared in full brilliancy through even a much thicker portion of the tail. The comet of 1828 possessed a nucleus about 528 miles in diameter, and yet Struve saw a star of the 11th magnitude through it, a fact which seems to justify the conclusion of Donati's comet on the 5th of October 1858, dabbing it, drawn from his own observations, that a comet has no influence upon the light of a star, and that stars of the 10th and 11th magnitude, and some even fainter, may be seen through their greatest mass without losing, in the smallest degree, either their light or their color. The nucleus of a comet is greatly affected both in size and density by its approach to the sun. But from the want of any sharply defined edge, it is difficult to measure its diameter with any accuracy. The comets of 1798 and 1805 each possessed a nucleus the diameter of which was 22 and 26 miles respectively. That of the Great Comet of 181 attained a diameter of 380 miles, while that of 1843 reached 680 miles, and the comet of 1845 as much as 468 miles. Donati's comet measured on the east of September 1858, 13,894 miles in diameter, while on the 25th of the same month it did not exceed 526 miles. The nebulous envelope, or coma, is also subject, July comet on the 2nd of July, 1861, to changes in form and size according as the comet approaches or recedes from the sun. It might be expected that the coma approaching the sun would expand and become rarefied by the extreme heat, but as in the nucleus, exactly the reverse has often been observed, in Encke's comet, for instance, in the year 1838. The diameter of the coma on the 9th of October was 480 miles. On the 25th of the same month, it was 616 miles. On the 23rd of November, it measured 302 miles, and on the 17th of December, it was only 338 miles. The tail is a prolongation of the coma, and is in most cases turned away from the sun, figure 211, whether the comet be approaching or receding from the sun in the course of its orbit. A drawing by Professor John Muller, given in figure 212, shows this position of the tail very clearly. In the map, the position of the sun is marked on the lower line to the right for the 27th of September, and the 8th and 14th of October, and these places are connected by straight lines with the places of the comet for those dates. The tail appears always curved, with the convex side turned towards the direction of the comet's motion. At the same time, this preceding edge is much more sharply defined than the concave side, just as if some resisting medium had impeded the advance of the tail and forced it back. But the tail does not always maintain this position. Comets have been observed position of the tail of a comet as regards the symbol, where the tail has been turned towards the sun, and others again possess several tails, all turned in opposite directions. As a comet approaches the sun, the tail regularly increases, from which it appears that the sun, whether by the action of heat or other means, contributes essentially to the formation of the tail and produces a separation of material particles from the head of the comet. The length of the tail is rarely less than 500 miles, and in some cases it extends as far as 100 or 150 miles. The breadth of the tail of the Great Comet of 181 at its widest part was nearly 1400 miles, the length 116,000, and that of the second comet of the same year even 140,000 miles. And yet the formation of the tail takes place in a very short space of time, often in a few weeks or even days. The influence exercised on the formation of the tail by its approach to the sun was shown in the comet of 1680, for at its perihelion it traveled at the rate of 1,216,800 miles in an hour, and as a consequence put forth a tail in 2 days 54 of 0 miles in length. It is easily conceivable that under such circumstances the mass of a comet must be exceedingly small. It is very probable that our Earth actually passed on the 30th of June, 1861, through part of the tail of the magnificent comet called the July comet, figure 213, which suddenly appeared in the heavens as if by magic on the 29th of June, and no indication of such a contact was evinced beyond a peculiar phosphorescence in the atmosphere, which was noticed by Mr. Hind, and also at the Liverpool Observatory. In the same way, the comet of 1776 passed among the satellites of Jupiter without disturbing their position in the slightest degree. This was not the case, however, with the comet, for the influence of the planet was so great on its small mass as to send it quite out of its course into an entirely new orbit, which it now accomplishes in about 20 years. We must now consider the remarkable phenomenon of a comet being divided into two parts, each part becoming a separate comet and pursuing an orbit of its own. Such an occurrence happened to Biela's comet while under observation in the year 1845. When observed on the 26th of November of that year, it appeared as a faint nebulous spot, not perfectly round, with an increased density towards the middle. On the 19th of December, it was rather more elongated, and 10 days later, it had become divided into two separate cloudy masses of equal dimensions, each furnished with a nucleus and tail, and for 3 months one followed the other at a distance of 1/10, subsequently 1/5, of the moon's diameter. The pair made their appearance again in August 1852, after having traveled together in one common orbit round the sun for more than 6 years and a half. But the distance between them had much increased, and from 154.0 miles, it had now reached 1,440 miles. Nor is this all. In conformity with its known period, the return of this comet was expected in the year 1850. And again in 1866, when it must have been visible from the Earth, as its path crossed the Earth's orbit at the place where the Earth was on the 30th of November. Notwithstanding the most diligent search, however, the comet could not be found, and it would seem that either, like Lexell's comet, it has been drawn out of its orbit by some member of the solar system, or else, as analogy suggests, it has ceased to be a comet, and has passed into some other form of existence. We must enter a little further than might seem needful for our purpose into the important phenomena observed in comets, partly by the naked eye, but more especially by the telescope, in order to obtain some ground for answering queries as to the physical nature of these heavenly bodies, as well as to acquire a standard by which to compare the facts collected by telescopic observation with those gathered by spectrum analysis. These questions are directed in the first place to the consideration of whether comets, like fixed stars and nebulae, are self-luminous, or whether, like planets, they shine by the reflected light of the sun. In the second place, to the consideration of their material composition and physical constitution. That the nucleus of a comet cannot be in itself a dark and solid body, such as the planets are, is proved by its transparency. But this does not preclude the possibility of its consisting of innumerable solid particles separated one from another, which, when illuminated by the sun, give by the reflection of the solar light the impression of a homogeneous mass. It has therefore been concluded that comets are either composed of a substance which, like gas in a state of extreme rarefaction, is perfectly transparent, or of small solid particles individually separated by intervening spaces through which the light of a star can pass without obstruction, and which, held together by mutual attraction, as well as by gravitation, towards a central denser conglomeration, moves through space like a cloud of dust. It is not impossible that comets without a nucleus are masses of gas at a white heat, of similar constitution to the nebulae, while those possessing a nucleus are composed of disengaged solid particles. In any case, the connection lately noticed by Schiaparelli between comets and meteor showers seems to necessitate the supposition that in many comets a similar aggregation of particles exists. It has been thought that the polarization of light furnished a means for ascertaining whether the light of an object was inherent or reflected, and supported by the observations made on the nuclei of comets for this purpose. The opinion has been confidently expressed that comets shine by reflected light, and not by any light of their own. But observations of this kind are in no way decisive, because in all polariscopes diffused irregularly reflected light AP pairs, just as little polarized as that given out by an independent source. Spectrum analysis could at once answer this question were a comet bright enough to form a complete spectrum. If the light of the comet were only reflected sunlight, the spectrum would then be like that of the moon and planets, a continuous one crossed by the Fraunhofer lines. But for the formation of such a spectrum, a very narrow slit is necessary, and none of the comets which have appeared within the last few years have been bright enough to allow of their spectra being examined with a close setting of the slit. On this point, therefore, the question remains at present undecided. Donati at Florence was the first to examine spectroscopically the light of comets. He compared the spectrum of the comet eye, 1864, with the spectra of metals in which the dark places were wider than the luminous parts, and he found that the entire spectrum consisted of 3 bright lines. Tempel's comet was observed in January 1866 by Secchi and Huggins, who found that it yielded a continuous spectrum exceedingly faint at the 2 ends, in which 3 bright lines were seen by the former observer, and only 1 by Huggins. The line seen by both observers was the brightest, and was situated about halfway between B and F of the solar spectrum. Secchi's view of this spectrum is given in figure 214. None of the 3 bright lines coincided with those of the nebula in Orion. It appears from this that the nucleus is at least partially self-luminous and is composed of gas in a luminous condition. On the other hand, the continuous spectrum proves that some of the light is reflected sunlight, for it cannot be admitted that the coma is formed of incandescent solid or liquid particles. The spectroscope gives no information as to the nature or condition of a substance from which we receive only reflected light. It is, however, probable that the coma and tail are of the same substance as the nucleus. These observations, therefore, yield no further result than that a gas in a state of luminosity is present in the comet, but that at the same time, either from this gas or from other portions of the comet which are non-luminous, sunlight is also reflected. In the years 1866 and 1867, Huggins observed the spectra of 2 small comets and found them to consist of a continuous spectrum as well as of one of bright lines. The light of these comets was therefore like Tempel's comet, composed partly of reflected light and partly of the comet's own light. The year 1868 brought the return of 2 periodic comets of greater brilliancy. The comet of Brorsen, I, and that of Winnicke, to Brorsen's comet, I, 1868, had in the telescope the appearance of a nearly circular nebula, in which the DEB-F spectra of Brorsen's and Winnicke's comets compared with the spectra of the Sun, carbon, and the nebulae. Brightness rapidly increased towards the center, but in which the existence of a nucleus was doubtful. There was only the faint trace of a tail, or more properly, merely a slight expansion of the coma. Secchi examined this comet with a simple direct vision spectroscope and compared the spectrum with that of Venus, bringing the planet and the comet alternately into the same place in the instrument. Huggins observed the same comet from the 2nd to the 13th of May and found with Secchi that the spectrum, figure 215, number 5, was discontinuous, consisting of 3 bright bands. The length showed that the light of the center of the head, as well as that of the coma, had entered the spectroscope. The brightest band of light was the middle one in the green, about halfway between the Fraunhofer lines B and F. When the sky was very favorable, this band was reduced to a single bright line of the apparent width of the comet's nucleus. The second band, less intense, but still very bright, was situated in the yellow-green, nearly in the middle of the space between the Fraunhofer lines B and D. Occasionally another band could be traced in the red, but it was difficult to fix its place. The third band was in the blue, towards the violet, about a third of the distance between F and G. An extremely faint light, not shown in the drawing, was apparent at the same time over the whole space of the spectrum, the indication of a very faint continuous spectrum. By narrowing the slit, these luminous bands could not be resolved into lines, which is the case with the bright bands of the nebula. It only produced a weakening of the bands of light until they completely disappeared. The spectrum of Brorsen's comet bears a great resemblance to that observed by Donati, but it differs essentially from the spectrum of a nebula, not only in its character, but also in the position of the bands of light. A comparison of these 2 spectra, number 5 and number 7, shows this at a glance. The comet PL 1868 was first observed on the night of the 13th-14th of June by Dr. Winnick in Karlsruhe, and soon attained sufficient brightness to be seen by the naked eye as a star of the 7th or 8th magnitude. The diameter of the coma, including the extremely faint luminous envelope, amounted to about the length of the tail being more than I degrees. The tail, as shown in Winnicki's comet 1868, seemed to have no connection with the bright nucleus. The following side, that turned away from the direction of motion, was sharply defined, while the other side gradually lost itself in space. When Secchi examined the comet on the 21st of June with a simple spectroscope without a slit, the spectrum was seen to consist of 3 brilliant bands of light, the brightest of which was in the green, another less bright in the yellow, and the faintest was situated in the blue. When this instrument was exchanged for one of Hoffmann's direct vision spectroscopes, the 3 bands were well defined, and the dispersed light had disappeared. On comparing the position of these lines with those exhibited by the spectra of various metals, it was found that the middle one lay very near to the magnesium line B, but the spectrum, as a whole, could not be brought to agree with that of any metal. He perceived, however, a great resemblance between the spectrum of the comet and that of carburetted hydrogen, which made him conclude that the light from the self-luminous pate of the comet was produced by that substance. Huggins investigated Winnicki's comet with a spectroscope consisting of 2 prisms of 60 degrees, and has given a drawing of the comet, figure 216, as well as of its spectrum, together with the spectra of the substances with which it was compared. In that of the electric spark in olive oil, no. The electric spark in olefiant gas, number 6, gives the principal lines of some of the substances brought into comparison by means of the electric spark. N equals nitrogen, O equals oxygen, Ng equals magnesium, A equals magnesium, equals sodium. The apparatus employed by Huggins for these comparisons is shown in figure 217. The olefiant gas was contained in the glass bottle A, from whence it flowed through the tube B, into which were soldered 2 platinum wires, E and F. At the place where the spark was to pass, a hole was bored through the glass tube, the edges of the opening carefully ground, and the opening closed by a smooth plate of glass. The light of the glowing gas was reflected by the small mirror C onto the reflecting prism in the interior of the tube, by which it was thrown on to the lower half of the slit, while the light of the comet was received upon the upper half. By this means, the spectrum of the olefiant gas produced by the electric spark was brought into close juxtaposition with the spectrum of the comet, so as to admit of an exact comparison. Secchi's observations have been completely confirmed by those of Huggins. The spectrum of the comet consisted of 3 broad, bright bands, which were sharply defined at the edge towards the red, but faded away gradually on the opposite side. Huggins, however, did not succeed in resolving the bands into sharp lines, but the middle and brightest band appeared to commence a well-defined bright line. When the slit was placed on the edge of the coma, the 3 bands were still distinguishable, 5700, but when the slit was directed to the fainter light of the tail, the spectrum appeared to be continuous. If the spectrum of the comet be compared with that of carbon, which has been disengaged from olive oil or olefiant gas by the heat of the electric spark, there is no great resemblance to be observed between them. The lines of hydrogen, moreover, belonging the spectrum of olefiant gas are not present in the spectrum of the comet. The same comet was spectroscopically observed by H.M.C. Wolf at Paris. It was remarked also by him that the 3 bright bands separated from each other by perfectly dark spaces could not be condensed into lines by narrowing the slit, and thus the spectrum offered no analogy to that of a nebula. The spectrum of the comet I 1870, Winnicke, was examined by Wolf and Rayet. It consisted, like the spectra of earlier comets, of 3 bright bands which spread out upon a continuous spectrum. Hash bands in the spectrum of the comet were like those obtained when olefiant gas is used, irresolvable into lines. The lines of the other component of olefiant gas, hydrogen, are omitted in the diagram. The lines of hydrogen were not visible in the spectrum of the comet. It appears to be right to consider this spectrum of bright bands to be that of carbon, and not that of any stable hydrocarbon, for Huggins found the same bands. Together with the lines of nitrogen when the spark was taken in cyanogen, and a spectrum essentially the same but less complete when compounds of carbon with oxygen were employed. On April 7, a faint comet was discovered by Dr. Winnick. I observed the comet on April 13, and May 2. On both days, the comet was exceedingly faint, and on May 2, it was rendered more difficult to observe by the light of the moon and a faint haze in the atmosphere. It presented the appearance of a small faint coma, with an extension in the direction from the sun. When observed in the spectroscope, I could detect the light of the coma to consist almost entirely of 3 bright bands. A fair measure was obtained of the center of the middle band, which was the brightest. It gives for this band a wavelength of about 510 millionths of a millimeter. I was not able to do more than estimate roughly the position of the less refrangible band. The result, it would be premature to draw decisive results from these comprehensive but as yet isolated observations. The spectrum of the 3 bright bands is derived unquestionably from the light of the comet's nucleus, and not from that of the coma, which is far too faint and ill-defined to produce such a spectrum. It may therefore be assumed that the nucleus is self-luminous, and that it is very possibly composed of glowing gas containing carbon. This theory has already been opposed by Przemysłowski, who instituted some experiments on light reflected from faintly illuminated strips of colored paper, and found that the spectrum of a body faintly illuminated by the sun presented exactly the same appearance which was observed by Secchi and Huggins in the comet of 1868. The spectrum of bands, therefore, given by this comet is not a proof of its being self-luminous, and even the light emitted by the nucleus may also be a reflected light. Secchi maintains, on the contrary, that the dark and bright absorption bands which are seen in the spectrum of light reflected from colored substances never have those sharp edges which are observed in the spectra of comets. In his fine polariscope, polarization was observed, gives 545 millionths. The third band was situated at about the same distance from the middle band on the more refrangible side. It would appear that this comet is similar in constitution to the comets which I examined in 1868, principally in the coma, and scarcely at all in the nucleus, which, had it reflected the sun's light, would have shown the greater amount of polarization. By collating these various phenomena, the conviction can scarcely be resisted that the nuclei of comets not only emit their own light, which is that of a glowing gas, but also, together with the coma and the tail, reflect the light of the sun. There seems, therefore, nothing to contradict the theory that the mass of a comet may be composed of minute solid bodies kept apart one from another in the same way as the infinitesimal particles forming a cloud of dust or smoke are held loosely together, and that as the comet approaches the sun, the most easily fusible constituents of these small bodies become wholly or partially vaporized, and in a condition of white heat overtake the remaining solid particles, and surround the nucleus in a self-luminous cloud of glowing vapor. Spectrum analysis will not be able to afford any more certain evidence regarding the physical nature of comets until the appearance of a really brilliant comet which can be examined in the various phases it may present. It would lead us too far from our purpose were we to describe more minutely the extremely interesting phenomena which the telescope has revealed of the separation of cometic matter, and the gradual formation of the coma and tail. Nor can we enter more fully here into the causes of the changes produced in the form of a comet by its approach to the sun, or to one of the larger planets, but we cannot pass over the extremely ingenious hypothesis brought forward by Professor Tyndall before the Philosophical Society of Cambridge on the 8th of March, 1869. This admirable investigator had already proved by a series of interesting experiments that concentrated solar light, or the electric light, decomposes the volatile vapors of many liquids, producing almost instantly a precipitate of cloudy matter, in which some very peculiar phenomena of light are displayed. The quantity of vapor may be so small as to escape detection, but the concentrated light falling upon it soon forms a blue cloud from the moving atoms of vapor which now become visible, and appear, according to the nature of the vapor, in a variety of forms as precipitations of matter on the beams of light. It is very striking in this experiment to see the astonishing amount of light that an infinitesimal amount of decomposable vapor is able to reflect. When the electric light is admitted into the tube, nothing is to be seen for the first moment. But soon a blue cloud shows itself, which is formed of almost infinitely small particles, either of vapor or, what is more probable, of the molecules set free to philosophical transactions, 1870 p. 323, Philosophical Magazine, 1869, number 249, Naturforscher's Suet number 33. By its decomposition, and after some minutes, the whole tube is filled with this blue color. The vaporous particles gradually augment in magnitude, and after some time, from 10 to 15 minutes, a dense white cloud fills the tube, which discharges so great a body of light that it is scarcely conceivable how so small a quantity of matter can possibly reflect so much light. Nothing, says Tyndall, could more perfectly illustrate that spiritual texture which Sir John Herschel ascribes to a comet than these actinic clouds. Indeed, the experiments prove that matter of almost infinite tenuity is competent to shed forth light far more intense than that of the tails of comets. Upon these facts, Tyndall has constructed a theory which offers an unforced explanation of many of the phenomena that have been observed, as, for instance, the formation and motion of the tail, etc., but which also stands in complete contradiction to many of the facts discovered by Schiaparelli. Chapter 69. Falling stars, meteor showers, balls of fire, and their spectra. Whoever has observed the heavens on a clear night with some amount of attention and patience cannot fail to have noticed the phenomenon of a falling star, one of those well-known fiery meteors which suddenly blaze forth in any quarter of the heavens, descend towards the earth, generally with great rapidity in either a vertical or slanting direction, and disappear after a few seconds at a higher or lower altitude. As a rule, falling stars can only be seen of an evening or at night, owing to the great brightness of daylight. But many instances have occurred in which their brilliancy has been so great as to render them visible in the daytime, as well when the sky was overcast as when it was perfectly cloudless. It has been calculated that the average number of these meteors passing through the Earth's atmosphere, and sufficiently bright to be seen at night with the naked eye, is not less than 7.5 million during the space of 24 hours. And this number must be increased to 400 million if those be included which a telescope would reveal. In many nights, however, the number of these meteors is so great that they pass over the heavens like flakes of snow, and for several hours are too numerous to be counted. Early in the morning of the 12th of November, 1799, Humboldt and Bonpland saw before sunrise, when on the coast of Mexico, thousands of meteors during the space of 4 hours, most of which left a track behind them of from 2 ionic degrees in length. They mostly disappeared without any display of sparks. But some seemed to burst, and others again had a nucleus as bright as Jupiter which emitted sparks. On the 12th of November, 1833, there fell another shower of meteors, in which, according to Arago's estimation, 240,000 passed over the heavens, as seen from the place of observation, in 3 hours. Only in very rare instances do these fiery substances fall upon the surface of the earth. When they do, they are called balls of fire, and occasionally they reach the earth before they are completely burnt out or evaporated. They are then termed meteoric stones, aerolites, or meteoric iron. They are also divided into accidental meteors and meteoric showers, according as to whether they traverse the heavens in every direction, or appear in great numbers following a common path, thus indicating that they are parts of a great whole. It is now generally received and placed almost beyond doubt by the recent observations of Schiaparelli, Leverrier, Weiss, and others, that these meteors, for the most part small, but weighing occasionally many tons, are fragmentary masses revolving, like the planets, round the sun, which in their course approach the earth, and drawn by its attraction into our atmosphere, are set on fire by the heat generated through the resistance offered by the compressed air. The chemical analysis of those meteors which have fallen to the earth in a half-burnt condition in the form of meteoric stones proves that they are composed only of terrestrial elements, which present a form and combination commonly met with in our planet. Their chief constituent is metallic iron, mixed with various silicious compounds. In combination with iron, nickel is always found, and sometimes also cobalt, copper, tin, and chromium. Among the silicates, olivine is especially worthy of remark as a mineral very abundant in volcanic rocks, as also at Egypt. There have also been found in the meteoric stones hitherto examined oxygen, hydrogen, sulfur, phosphorus, carbon, aluminium, magnesium, calcium, sodium, potassium, manganese, titanium, lead, lithium, and strontium. The height at which meteors appear is very various, and ranges chiefly between the limits of 46 and 92 miles. The mean may be taken at miles. The speed at which they travel is also various, generally about half as fast again as that of the Earth's motion around the Sun, or about miles in a second. The maximum and minimum differ greatly from this amount, the velocity of some meteor at 14 miles, and that of others at 107 miles in a second. When a dark meteorite of this kind, having a velocity of 660 miles per minute, encounters the Earth, flying through space at a mean rate of 140 miles per minute, and when through the Earth's attraction its velocity is further increased 230 miles per minute, this body meets with such a degree of resistance, even in the highest and most rarefied state of our atmosphere, that it is impeded in its course and loses in a very short time a considerable part of its momentum. By this encounter there follows a result common to all bodies, which, while in motion, suddenly experience a check. When a wheel revolves very rapidly, the axle-tree or the drag, which is placed under the wheel, is made red hot by the friction. When a cannon ball strikes suddenly with great velocity against a plate of iron, which constantly happens at target practice, a spark is seen to flash from the ball even in daylight. Under similar circumstances, a lead bullet becomes partially melted. The heat of a body consists in the vibratory motion of its smallest particles. An increase of this molecular motion is synonymous with a higher temperature. A lessening of this vibration is termed decreasing heat, or the process of cooling. Now, if a body in motion, as for instance a cannonball, strike against an iron plate or a meteorite against the Earth's atmosphere, in proportion as the motion of the body diminishes and the external action of the moving mass becomes annihilated by the pressure of the opposing medium upon the foremost molecules, the vibration of these particles increases. This motion is immediately communicated to the rest of the mass, and by the acceleration of this vibration, through all the particles, the temperature of the body is raised. This phenomenon, which always takes place when the motion of a body is interrupted, is designated by the expression, the conversion of the motion of the mass into molecular action or heat. It is a law without exception that where the external motion of the mass is diminished, an interaction among its particles or heat is set up in its place as an equivalent, and it may be easily supposed that even in the highest and most rarefied strata of the Earth's atmosphere, the velocity of the meteorite would be rapidly diminished by its opposing action, so that shortly after entering our atmosphere, the vibration of the inner particles would become accelerated to such a degree as to raise them to a white heat, when they would either become partially fused, or if the meteorite were sufficiently small, it would be dissipated into vapor and leave a luminous track behind it of glowing vapors. Haidinger, in a theory embracing all the phenomena of meteorites, explains the formation of a ball of fire around the meteor by supposing that the meteorite, in consequence of its rapid motion through the atmosphere, presses the air before it till it becomes luminous. The compressed air, in which the solid particles of the surface of the meteorite glow, then rushes on all sides, but especially over the surface of the meteor behind it, where it encloses a pear-shaped vacuum which has been left by the meteorite, and so appears to the observer as a ball of fire. If several bodies enter the Earth's atmosphere in this way at the same time, the largest among them precedes the others, because the air offers the least resistance to its proportionately smallest surface. The rest follow in the track of the first meteor, which is the only one surrounded by a ball of fire. When by the resistance of the air the motion of the meteor is arrested, it remains for a moment perfectly still. The ball of fire is extinguished. The surrounding air rushes suddenly into the vacuum behind the meteor, which, left solely to the action of gravitation, falls vertically to the Earth. The loud detonating noise usually accompanying this phenomenon finds an easy explanation in the violent concussion of the air behind the meteor. While the generally received theory that the detonating noise is the result of an explosion or bursting of the meteorite does not meet with any confirmation. The circumstance that most meteors are extinguished before reaching the Earth seems to show that their mass is but small. If the distance of a meteor from the Earth be ascertained, as well as its apparent brightness as compared with that of a planet, it is possible, by comparing its luminosity with that of a known quantity of ignited gas, to estimate the degree of heat evolved in the meteor's combustion. As this heat originates from the motion of the meteor being impeded or interrupted by the resistance of the air, and as this motion or momentum is exclusively dependent on the speed of the meteor, as well as upon its mass, it is possible, when the rate of motion has been ascertained by direct observation, to determine the mass. Professor Alexander Herschel has calculated by this means that those meteors of the 9th and 10th of August 1863, which equaled the brilliancy of Venus and Jupiter, must have possessed a mass of from 5 to 8 pounds, while those which were only as bright as stars of the 2nd or 3rd magnitude would not be more than about 90 grains in weight. As the greater number of meteors are less bright than stars of the 2nd magnitude, the faint meteors must weigh only a few grains, for according to Professor Herschel's computation, the 5 meteors observed on the 12th of November, 1865, some of which surpassed in brilliancy stars of the 1st magnitude, had not an average weight of more than 5 grains, and Schiaparelli estimated the weight of a meteor from other phenomena to be about 15 grains, the mass. However, of the meteoric stones which fall to the earth is considerably greater whether they consist of one single piece, such as the celebrated ironstone discovered by Pallas in Siberia, which weighed about 20 pounds, or of a cloud composed of many small bodies which penetrate the earth's atmosphere in parallel paths, as shown in and descend upon the earth, present the appearance of a large meteor bursting into several smaller pieces. Such a shower of stones, accompanied by a bright light and loud explosion, occurred at L'Aigle in Normandy on the 26th of April, 1803, when the number of stones found in a space of 14 square miles exceeded 20. In the meteoric shower that fell at Kőhainga in Hungary on the 9th of June, 1866, the principal stone weighed about 800 pounds and was accompanied by about 1,000 smaller stones, which were strewed over an area of 9 miles in length by 3 broad. It must not be supposed, however, that the density of such a cosmical cloud is as great when out of the reach of the attraction of the sun and the earth as when its constituents fall upon the earth's surface. Schiaparelli calculates, from the number of meteors observed yearly in the month of August, that the distance between any two must amount, on the average, to 460 miles. As the cosmical clouds which produce the meteors approach the sun in their wanderings from the far-off regions of space, they increase in density some million times. Therefore, the distance between any two meteors, only a few grains in weight, before the cloud begins to be condensed, may be upwards of 40 miles. The most striking example of such a cosmical cloud, composed of small bodies loosely hung together and existing with hardly any connection one with another, is exhibited in the meteoric showers occurring periodically in August and November. It is an ascertained fact that on certain nights in the year the number of meteors is extraordinarily great, and that at these times they shoot out from certain fixed points in the heavens. The shower of meteors, which happens every year on the night of the 10th of August, proceeding from the constellation of Perseus, is mentioned in many old writings. The shower of the 1, 2nd, and 13th of November occurs periodically every 33 years, for 3 years succession with diminishing numbers. It was this shower that Alexander von Humboldt and Bonpland observed on the 1/2 of November 1799 as a real rain of fire. It recurred on the 12th of November 1833 in such force that Arago compared it to a fall of snow, and was lately observed again in its customary splendor in North America on the 14th of November 1867. Besides these two principal showers, there are almost 100 others recurring at regular intervals. Each of these is a cosmical cloud composed of small dark bodies very loosely held together, like the particles of a sand cloud, which circulate round the sun in one common orbit. The orbits of these meteor streams are very diverse. They do not lie approximately in one plane like those of the planets, but cross the plane of the Earth's orbit at widely different angles. The motion of the individual meteors ensues in the same direction in one and the same orbit, but this direction is in some orbits in conformity with that of the Earth and planets, while in others it is in the reverse orbit. The Earth in its revolution round the sun occupies every day a different place in the universe. If, therefore, a meteoric shower passed through our atmosphere at regular intervals, there must be at the place where the Earth is at that time an accumulation of these small cosmical bodies, which, attracted by the Earth, penetrate its atmosphere, are ignited by the resistance of the air, and become visible as falling stars. A cosmical cloud, however, cannot remain at a fixed spot in our solar system, but must circulate round the sun as planets and comets do, whence it follows that the path of the periodic shower intersects the Earth's orbit, and the Earth must either be passing through the cloud or else very near to it, when the meteors are visible to us. The meteor shower of the 10th of August, the radiant point of which is situated in the constellation of Perseus, takes place nearly every year with varying splendor. We may therefore conclude that the small meteors composing this group form a ring round the sun, and the Earth every 10th of August is at the spot where this ring intersects our orbit. Also, that the ring of meteors is not equally dense in all parts. Here and there, these small bodies must be very thinly scattered, and in some places even altogether wanting orbit which this meteoric mass describes around the sun. The Earth encounters this orbit on the 10th of August and goes straight through the ring of meteors. The dots along the ring indicate the small dark meteors which ignite in our atmosphere and are visible as shooting stars. The line M is the line of intersection of the Earth's orbit and that of the meteors. The line PS shows the direction of the major axis of their orbit. This axis is 50 times greater than the mean diameter of the Earth's orbit. The orbit of the meteors is inclined to that of the Earth at an angle of 64 degrees 3, and their motion is retrograde or contrary to that of the Earth. The November shower is not observed to take place every year on the 12th or 13th of that month, but it is found that every 33 years an extraordinary shower occurs on those days. Proceeding from a point orbit of the meteor shower of the Loth of August, in the constellation of Leo, the meteors composing this shower, unlike the August one, are not distributed along the whole course of their orbit, so as to form a ring entirely filled with meteoric particles, but constitute a dense cloud of an elongated form, which completes its revolution round the sun in 33 years, and crosses the Earth's path at that point where the Earth is every 13th of November, when the November shower reappears after the lapse of 33 years. The phenomena is repeated during the 2 following years on the 13th of that month, but with diminished splendor. The meteors, therefore, extend so far along the orbit as to require 3 years before they have all crossed the Earth's path at the place of intersection. They are besides unequally distributed, the preceding part being much the most dense. A very small part of the elliptic orbit and the distribution of the meteors during the November shower is represented in figure 220. As shown in the drawing, this orbit intersects that of the Earth at the place where the Earth is about the 14th of November, and the motion of the meteors, which occupy only a small part of their orbit and are very unequally distributed, is retrograde. Or contrary to that of the Earth, the inclination of this orbit to that of the Earth is only 17 degrees 44. Its major axis is about 10 1/3 times greater than the diameter of the Earth's orbit, and the period of revolution for the densest part of the meteorites round the sun is 33 years 3 months. From all we have now learned concerning the nature and constitution of comets, nebulae, cosmical clouds, and meteoric swarms, an unmistakable resemblance will be remarked among these different forms in space. The affinity between comets and meteors had been already recognized by Chladni, but Schiaparelli of Milan was the first to take account of all the phenomena exhibited by these mysterious heavenly bodies, and with wonderful acuteness to treat successfully the mass of observations and calculations which had been contributed during the course of the last few years by Opolzer, Peters, Bruns, Heiss, Leverrier, and other observers. He not only shows that the orbits of meteors are quite coincident with those of comets, and that the same object may appear to us at one time as a comet and at another as a shower of meteors, but he proves also by a highly elegant mathematical calculation that the scattered cosmic masses known to us by the name of nebulae would, if in their journey through the universe they were to come within the powerful attraction of our sun, be formed into comets, and these again into meteoric showers. We should be carried away too far from our subject were we to enter fully into the consideration of this bold and ingenious theory of the Milan astronomer, supported though it be by a series of facts. But while we refer the reader to Volpizzo, of Naturwissenschaftlichen Volksbücher by A. Bernstein, in which this subject Die Rätsel der Sternschnuppen und der Kometen is fully treated of in a very clear and attractive manner, we shall confine ourselves to the following short statement of Schiaparelli's theory. Nebulae are composed of cosmic matter, in which as yet there is no central point of concentration, and which has not become sufficiently dense to form a celestial body in the ordinary sense of the term. The diffuse substance of these cosmic clouds is very loosely hung together. Its particles are widely separated, thus constituting masses of enormous extent, some of which have taken a regular form and some not. As these nebulous clouds may be supposed to have, like our sun, a motion in space, it will sometimes happen that such a cloud comes within reach of the power of attraction of our sun. The attraction acts more powerfully on the preceding part of the nebula than on the further and following portion, and the nebula, while still at a great distance, begins to lose its original spherical form, and becomes considerably elongated. Other portions of the nebulous mass follow continuously the preceding part, until the sphere is converted into a long cylinder, the foremost part of which, that towards the sun, is denser and more pointed than the following part, which retains a portion of its original breadth. As it nears the sun, this transformation of the nebulous cloud becomes more complete. Illuminated by the sun, the preceding part appears to us as a dense nucleus, and the FQOing part, turned away from the sun, as a long tail curved in consequence of the lateral motion preserved by the nebula during its progress. Out of the original spherical nebula, quite unconnected with our solar system, a comet has been formed, which, in its altered condition, will either pass through our system to wander again in space, or else remain as a permanent member of our planetary system. The form of the orbit in which it moves depends on the original speed of the cloud, its distance from the sun, and the direction of its motion, and thus its path may be elliptical, hyperbolical, or parabolical. In the last two cases, the comet appears only once in our system, and then seturns to wander in the realms of space. In the former case, it abides with us, and accomplishes its course round the sun, like the planets, in a certain fixed period of years. From this, it is evident that the orbits of comets may occur at every possible angle to that of the Earth, and that their motion will be sometimes progressive and sometimes retrograde. The history of the cosmical cloud does not, however, end with its transformation into a comet. Schiaparelli shows in a striking manner that, as a comet is not a solid mass, but consists of particles each possessing an independent motion, the head or nucleus nearer the sun must necessarily complete its orbit in less time than the more distant portions of the tail. The tail will therefore lag behind the nucleus in the course of the comet's revolution, and the comet, becoming more and more elongated, will at last be either partially or entirely resolved into a ring of meteors. In this way, the whole path of the comet becomes strewn with portions of its mass, with those small dark meteoric bodies which, when penetrating the Earth's atmosphere, become luminous and appear as falling stars. Instead of the comet, there now revolves round the sun a broad ring of meteorae, stones which occasion the phenomena we every year observe as the August meteors, whether this ring be continuous, and the meteoric masses strewn along the whole course of the path of the original comet, or whether the individual meteors, as in the November shower, have not filled up entirely the whole orbit, but are still partially in the form of a comet, is in the transformation of a cosmical cloud through the influence of the sun only a question of time. In course of years, the matter composing a comet, which describes an orbit round the sun, must be dispersed over its whole path. If the original orbit be elliptical, an elliptic ring of meteors will gradually be formed from the substance of the comet of the same size and form as the original orbit. Schiaparelli has in fact discovered so close a resemblance between the path of the August meteors and that of the comet of 1862, number 3, that there cannot be any doubt as to their complete identity. The meteors to which we owe the annual display of falling stars on the 10th of August are not distributed equally along the whole course of their orbit. It is still possible to distinguish the agglomeration of meteoric particles which originally formed the cometary nucleus from the other, less dense parts of the comet. Thus, in the year 1862, the denser portion of this ring of meteors through which the Earth passes annually on the 10th of August, and which causes the display of falling stars, was seen in the form of a comet. With head and tail as the densest parts approached the Sun and Earth in the course of that month, a poser of Vienna calculated with great accuracy the orbit of this comet, which was visible to the naked eye. Schiaparelli had previously calculated the orbit of the meteoric ring to which the shooting stars of the 10th of August belong before they are drawn into the Earth's atmosphere. The almost perfect identity of the two orbits justifies Schiaparelli in the bold assertion that the comet of 1862, Nova 3, is no other than the remains of the comet out of which the meteoric ring of the 10H of August has been formed in the course of time. The difference between the comet's nucleus and its tail that has now been formed into a ring consists in that while the denser meteoric mass forming the head approaches so near the Earth once in every 120 years as to be visible in the reflected light of the sun, the more widely scattered portion of the tail composing the ring remains invisible, even though the Earth passes through it annually on the Ioth of August. Only fragments of this ring, composed of dark meteoric particles, become visible as shooting stars when they penetrate our atmosphere by the attraction of the Earth and ignite by the compression of the air. A cloud of meteors of such a character can naturally only be observed as a meteor shower when in the nodes of its orbit. That is to say, in those points where it crosses the Earth's orbit, and then only when the Earth is also there at the same time, so that the meteors pass through our atmosphere. The nebula coming within the sphere of attraction of our solar system would, at its nearest approach to the Sun, perihelion, and in the neighboring portions of its orbit, appear as a comet, and when it grazed the wreath's atmosphere would be seen as a shower of meteors. Calculation shows that this ring of meteors is about 10,948 millions of miles in its greatest diameter. As the meteoric shower of the Ioth of August lasts about 6 hours, and the Earth travels at the rate of 18 miles in a second, it follows that the breadth of this ring, at the place where the Earth crosses it, is 443,520 miles. In figure 221, AB represents a portion of the orbit of the comet of 1862, Nova 3, which is identical with that, figure 219, of the August shower, orbits of comets 362. And 1866, the calculations of Schiaparelli, Opolzer, Peters, and Leverrier have also discovered the comet producing the meteors of the November shower and have found it in the small comet of 1866. First observed by Temple of Marseilles, its transformation into a ring of meteors has not proceeded nearly so far as that of the comet of 1862. Its existence is of a much more recent date, and therefore the dispersion of the meteoric particles along the orbit and the consequent formation of the ring is but slightly developed. According to Leverrier, a cosmical nebulous cloud entered our system in January 126 and passed so near the planet Uranus as to be brought by its attraction into an elliptic orbit round the Sun. This orbit is the same as that of the comet discovered by Temple and calculated by Opolzer, and is identical with that in which the November group of meteors make their revolution. Since that time, this cosmical cloud, in the form of a comet, has completed 52 revolutions round the Sun without its existence being otherwise made known than by the loss of an immense number of its components in the form of shooting stars as it crossed the Earth's path in each revolution, or in the month of November in every 33 years. It was only in its last revolution, in the year 1866, that this meteoric cloud, now forming part of our solar system, was first seen as a comet. The orbit of this comet is much smaller than that of the August meteors, extending at the aphelion as far as the orbit of Uranus, while the perihelion is nearly as far from the Sun as our Earth. The comet completes its revolution in about 33 years and 3 months, and encounters the Earth's orbit as it is approaching the Sun towards the end of September. It is followed by a large group of small meteoric bodies, which form a very broad and long tail, through which the Earth passes on the 13th of November. Those particles which come in contact with the Earth, or approach so near as to be attracted into its atmosphere, become ignited and appear as falling stars. As the Earth encounters the comet's tail, or meteoric shower, for 3 successive years at the same place, we must conclude the comet's track to have the enormous length of 1,772 millions of miles. In Figure 221, CD represents a portion of the orbit of this comet which is identical with the orbit, Figure 220, of the November meteors. By the side of these important conclusions, which the observation and acuteness of modern astronomers have been able to make concerning the nature and mutual connection of nebulae, comets, meteors, and balls of fire, the results of spectrum analysis, as applied to meteors, will seem to be exceedingly scant. This is easy to understand when we reflect how rapidly these fiery meteors rush through our atmosphere, and how difficult it is to lay hold of them with the spectroscope during their instantaneous apparition. Before the instrument can be directed to a meteor or ball of fire, and the focus adjusted, the object has disappeared from view. The application, therefore, of spectrum analysis to these fleeting visitors is left almost entirely to chance, and is mainly confined to those nights in which yearly or at certain known periods an extraordinary shower of falling stars is expected to occur. In the year 1865, Alexander Herschel drew attention to the expected fall of meteors in the ensuing year and suggested that they should be observed with the spectroscope, on the ground that some few spectroscopic observations previously made had shown the spectrum of a meteor to be a continuous one, without any dark lines. Browning, a master in the art of constructing the spectrum apparatus, undertook the investigation, and observed in the nights of the 9th and 10th of August, as well as during the early morning hours of the 14th of November, at his observatory at Upper Holloway, near London, as many as 70 spectra of meteors and their trains. The hand spectroscope of Huggins, described at P480, and represented in Figure 173, as constructed by Browning for the direct observation of the solar appendages during an eclipse. It is well adapted for these investigations, but a still better instrument is that drawn in Figure 222, specially constructed by Browning for his own use in the observation of meteors, in which the apparent angle caused by the velocity of the meteor is diminished, and which, on account of the large field of view, greatly facilitates the observation of a falling star. This instrument consists of a direct vision compound prism P and a plano-concave cylindrical lens LD. MJ-M2, M3 denote 3. Successive places in the flight of a meteor, and ML9M2 show the path of the rays from the meteor to the lens L, while the dotted lines indicate the course taken by the rays in their passage through the refracting media. The ray reaches the eye, viewing it through the prism at the same moment as the ray moves. The eye, therefore, commands the large space in the heavens included between M and 3, and can observe accordingly a meteor shooting over that space without the instrument being moved. In such a spectroscope, the meteor appears to be stationary, and its spectrum can be observed without difficulty. Browning was able with this instrument to observe the spectra of some fireballs thrown into the air only a few feet from him. Although the angular velocity of such balls was very great, yet the characteristic lines of their component metals, barium, strontium, etc., were very clearly seen. If a biconcave lens of longer focus than the cylindrical lens be placed immediately in front of L and turned towards the heavens, rays of a still greater convergence, reaching beyond M and M3, will be brought within the range of the eye, and the field of view of the instrument considerably increased by this means. Instead of observing the spectrum with the unassisted eye, a small telescope may be employed, the position and direction of which, with regard to the prisms, is represented in Figure 173. Browning directed the instrument to that point in the heavens whence the meteors proceeded, and thus succeeded in retaining a few of the great number that fell in the field of the spectroscope, and observing the character of their spectra. The spectra of the heads of the meteors were mostly continuous, in which all the prismatic colors of the solar spectrum were visible excepting violet. In certain instances, however, the yellow preponderated in the spectrum. In others, the spectrum consisted almost entirely of one homogeneous yellow hue, though nearly every other color, from green, was very faintly visible. In 2 instances, the spectrum presented a homogeneous green tint. No remarkable difference in the light of the nuclei of the August and November meteors was perceptible. In most of the August meteors, only one yellow CW line of intense brilliancy remained in the spectrum of the tail or track of light left behind when it began to dissipate, the unmistakable sign of the presence of luminous gas, a line which could only be compared to the line of glowing sodium. In the November meteors, on the contrary, the spectrum of the train was characterized by continuity and breadth, but by a deficiency of color, the light which was mostly blue. Green, or steel gray, appeared in general to be homogeneous, but this appearance might arise from the light being too weak to yield a visible spectrum, as in the case of stars below the 2nd and 3rd magnitude. Where the red and blue rays are wanting in the spectrum, though doubtless present in the light of the star, the yellow line given by the train of the August meteors was altogether absent in that of the November meteors. The principal result of these investigations is confined, therefore, to the establishment of the fact that meteors consist of incandescent solid bodies, and that difference is discernible in the chemical composition of the August and November meteoric showers. The November shower of 1868 was observed by Secchi. Among the numerous meteors that left a train of light behind them was one the track of which lasted 15 minutes, and was at first sufficiently bright to allow of examination by a prism. Secchi found the spectrum to be discontinuous, and the principal bright bands and lines were red, yellow, green, and blue. Besides this observation, Secchi was so fortunate as to see 2 meteors in the spectroscope. The magnesium line appeared with great distinctness, besides which some lines were also seen in the red. On account of the great difficulty of observing meteors with a narrow setting of the slit, ordinary spectroscopes are not suited to this purpose. The hand spectroscope, described at P480, however, cannot show any sharp lines, even when the meteor contains elements which in an ordinary spectroscope would yield bright lines. The only resource, therefore, is to substitute a cylindrical lens for the slit, and there can be no doubt that an apparatus of this kind will be employed in future with great success in the investigation of meteors by means of spectrum analysis. Chapter 70. Spectrum of lightning, from the close connection between lightning and the electric spark. It was to be anticipated that a flash of lightning would yield a spectrum closely allied to that of the ordinary electric discharge when passed through the air, and that it would therefore consist of the bright lines belonging to the atmospheric air, and therefore preeminently those of nitrogen. This was in fact proved to be the case by Captain Herschel during a storm when the flashes of lightning were very numerous, on which occasion he found, by the use of a hand spectroscope, Figure 172, that among the numberless bright lines visible, the blue nitrogen line was the brightest, while the red line of hydrogen, HGRA, was also present. Besides this spectrum of lines, there was visible at the same time a bright continuous spectrum exhibiting the principal colors. The ordinary spectrum of lightning produces the impression of green and blue, or rather of greenish blue. But as in bright flashes, all the prismatic colors are visible, it must be supposed that the part between the lines E and F is so much brighter than the rest as to cause the impression of those colors to predominate in the spectrum. The variation of relative brightness of the continuous spectrum and of the spectrum of lines is very surprising. At times the lines are scarcely visible, and at other times, with the exception of the lines, there is scarcely any spectrum to be seen. The difficulty of distinguishing the many fainter lines is considerably increased by the instantaneous character of the phenomenon. Before a certain line has been selected, the faint impression upon the retina has disappeared, and the remembrance of the line half determined upon has passed away before another flash succeeds, so that there remains no standard of comparison. The most complete observations that have yet been made on the spectra of lightning are those by Professor Kundt of Zurich, by whom upwards of 50 flashes of lightning have at different times been observed with a pocket spectroscope. In addition to the spectra consisting of bright lines, there always appeared other spectra formed of a great number of fainter bands, somewhat broader than the lines, and disposed regularly at equal intervals one from another. The spectra of lines consisted of one and sometimes of two lines in the extreme red, a few very bright lines in the green, and some less bright in the blue, besides a still greater number much fainter, most of which, however, were sharply defined. The spectra of different flashes were so far different that while certain lines were very brilliant in one flash, they were entirely wanting in another, where they were replaced by a set of lines which were invisible in many other flashes. The spectra of bands were quite as dissimilar, the colored bands in some flashes appearing in the blue and violet, in others in the green as well, and occasionally only in the red. In most cases, each flash had only one of these spectra. The spectra of lines were usually given by the forked flashes, while sheet lightning yielded the spectra of bands. In only 2 cases did the same flash first give a bright spectrum of lines very sharply defined, and then suddenly show a spectrum of bands evenly distributed throughout. The 2 kinds of spectra correspond with the different colors in which both descriptions of lightning appear to the unassisted eye. The light of forked lightning is usually white, while that of sheet lightning is mostly red, but sometimes violet and bluish. This is in conformity with the different colors exhibited by the discharges of electrical machines, according to the form in which they appear, whether as a spark or a brush of light. While the light of a spark discharged into the air is more or less white according to the nature of the bodies between which it passes, the color of the electric brush is red or violet, and that of the electric glow is violet or bluish. The light of the electric spark always gives a spectrum of lines, while that of the brush or glow discharge exhibits a spectrum of bands. The investigations of Kundt lead to the conclusion that the difference in the spectra of lightning depends upon the mode in which the electricity in the atmosphere is discharged, whether through the earth or between the clouds. When an electric cloud discharges itself into the earth, the discharge occurs at a state of high tension, and accompanied by a great development of heat, darts to the ground in the form of a forked flash, passing on its way through the atmospheric air, that is to say, through a gaseous mixture of oxygen, nitrogen, watery vapor, and carbonic acid. According as one or other or several together of these gases are raised by the flash to a glowing state, the spectrum of the lightning assumes a different form. When, on the contrary, the discharge takes place from one cloud into another, it occurs usually in the form of a brush, because in consequence of the previous electrical attraction, both clouds have received pointed and indented forms, and in such circumstances a high degree of tension is rarely attained, and the current frequently passes as a rapid succession of discharges, which take the form of a brush of light. The various kinds of electrical discharges are accompanied by a corresponding variety in the report. If in the form of a spark, it is well known that a single sharp crack is heard. The brush discharge is never accompanied by a single clap, but always by a hissing or rushing noise with a series of faint cracks in rapid succession. The glow discharge is perfectly noiseless. All these phenomena lead to a simple explanation of the various kinds of lightning whether in the form of forked flashes, sheet lightning, or summer lightning, as well as of the sounds by which they are accompanied of the simple clap and the peal of thunder. But the few observations yet made upon the spectra of lightning suggest a number of questions which can only be answered by a series of additional observations. Chapter 71. Spectrum of the Aurora Borealis. The splendid phenomena exhibited by a brilliant display of the Aurora Borealis are always accompanied by a greater or less disturbance of the magnetic needle, so that the aurora has long been supposed to be occasioned by the noiseless passage of electricity through the rarefied portions of the upper regions of the atmosphere, a kind of glow discharge or electric display, such as is exhibited by discharging a quantity of electricity through a Geissler's tube filled with highly rarefied air. Angstrom spectrum observations of this object do not seem to confirm this conjecture, for the luminous arch skirting the dark segment and never absent in a faint show of aurora gives a spectrum of one bright line situated to the left of the well-known calcium group of the solar spectrum. Besides this comparatively very intense line, Angstrom observed, with a wider slit, traces of three very faint bands reaching nearly to the Fraunhofer F line. But only once did faint lines appear in this region during the undulations of a very flickering arch. The light of the Aurora Borealis is therefore almost homogeneous, monochromatic. A special interest attaches to these observations, made in the winter of 1867 to 68, from the circumstance that the zodiacal light gave the same line as observed by Angstrom for a week together in March 1867 at Uppsala, where it was seen with remarkable intensity for that latitude, and in one brilliant starlight night when the whole heavens appeared to be phosphorescent. Traces of this homogeneous light were visible in the spectroscope. From the faint light proceeding from all parts of the sky, the bright line mentioned above, the place of which has been determined by Struve to be number 1259 of Kirchhoff's scale, between D and anywhere, with a probable error of 10 or 15 units, corresponds, according to Angstrom, to a wavelength of 5/567 of a millimeter, and is not coincident with any known line of a terrestrial element. This line is introduced into Angstrom's spectrum of the telluric lines, figure 95, as a dotted line between pound and E at 556. The display of Aurora Borealis on the 15th of April, 1869, visible in Western Europe, Russia, and America, and which at New York exhibited an appearance of extraordinary beauty, was observed there by Professor Winlock, with the spectroscope in opposition to the observations made in Europe. He found the spectrum to consist of 5 bright lines, the positions of which he has determined according to Huygens scale to be 1280, 1400, 1550, 1680, and 2640. The divisions of Kirchhoff's scale 1247, 1351, and 1473 correspond to the first 3 numbers. Consequently, Winlock's spectrum of the aurora approaches very closely the representation given the spectrum of the corona number 2, and that of the prominences number 1, as observed by Young in the total eclipse of the 7th of August, 1869. Of these lines, the third, 1474 K, is the brightest. The spectrum of the aurora has been repeatedly observed in America by D.K. Winder. A bright line in the yellow was nearly always seen by him close to D, but less refrangible, and was coincident with one of the dark lines in the telluric group, which appears in the solar spectrum when the sun is near the horizon. Beside this line, there was a fainter one in the green, and on one occasion a line appeared also in the red. The Aurora Borealis was observed by Rayet and Sorel on the 15th and 16th of April, 1869, when the spectrum showed very clearly the characteristic auroral line, wavelength 5,567 10/millionth of a millimeter, angstrom, as well as the atmospheric lines. The aurora of the 6th of October, 1869, was examined by Vogel with the spectroscope. On this occasion also the light appeared to be homogeneous, though with a moderate opening of the slit. The spectrum showed only the yellow characteristic line. the position of which was estimated at about 1230 K when the slit was opened as much as 1 P3 millimeter. A faint green light made its appearance, which was roughly estimated to extend as far as the F-line. This light could not be concentrated into a line of light by any contraction of the slit. No such faint light was perceptible in the direction of the red, a fact which precludes the possibility of this light being occasioned by some stellar light finding its way into the spectroscope through the slit. On the 5th of April, 1870, a display of the aurora was examined by A. Schmidt at Lennep, Rhenish provinces. The spectrum here again consisted of one remarkably bright and broad line, somewhat to the right of D towards E, which varied in intensity, at times appearing very faint, and immediately afterwards shining out with great brilliance. From the neighborhood of this line to F, there stretched a continuous band, which became resolved frequently into 3 lines, bright though fainter than the first line. A magnificent exhibition of the aurora borealis was visible on the 24th and 25th of October, 1870, over the greater part of Europe, which for beauty and extent has hardly ever been exceeded in this portion of the globe. On the 24th of October, it extended over the northern and western portions of the sky, and covered more than a fourth of the whole horizon. Upon the luminous red background there appeared 3 deep red streamers very sharply defined, to which the cloudless heavens and the brilliancy of the stars upon the red sky gave an additional splendor. On the 25th of October, the phenomena offered the rare spectacle of an auroral crown. A number of flaming streamers of the aurora, which shot out on all sides, were united at a point in the heavens a little to the south of the zenith. On that evening, all the large streamers, most of which were of a crimson hue, crossed by white rays, converged towards that central point, which preserved unchanged its position with regard to the horizon. Professor Förster, Berlin, found that the spectrum of the aurora of the 25th of October consisted only of the same narrow greenish-yellow band of light, the position of which has been already determined, and which is not coincident with any of the lines of known elements. In those portions, however, of the sky which to the eye seemed unilluminated, the spectroscope revealed very clearly the characteristic line of the aurora. Dr. Tietjen states that some weeks previously, in the same observatory, upon evenings when no trace of aurora was visible, the spectroscope showed the same line in several places in the sky on the same evening. Kepron at Guildford observed in the spectrum of the aurora a very bright line in the green, which was distinctly visible in all parts of the sky, but which appeared with remarkable brilliancy in the silver-white rays of the aurora. Besides this line, there was also a much fainter line in the red, which is the lithium line. An observer at St. Mary Church, Torquay, describes the spectrum as consisting of 4 lines in the red and 1 line in the green. Of these, a strongly marked red line was near C, a strongly marked pale yellow line near D, a paler one near F, and a still fainter one beyond. There was also a faint continuous spectrum that extended from D to beyond lines. In position and color it lay between the red lines of lithium and calcium. The observer is of opinion that 2 spectra were here superposed, one produced by the red rays, consisting of the 4 lines and the faint continuous spectrum, the other given by the remaining light, showing the greenish line near D. Gibbs, observing in London on the same evening, saw only a line in the red very similar to the C line, HA, and another line in the pale green part of the spectrum. Eiger, in Bedford, also observed a red band near C, a very bright white band near D. Apparently, the characteristic line of the aurora mentioned before as being visible on the 25th of October, in every portion of the sky, a faint and ill-defined line near F, as well as an exceedingly faint line about midway between these last 2 lines. The red band was absent from the spectrum of the white rays of the aurora, whereas the remaining 3 lines were always visible. These observations established the supposition that the different rays of the aurora borealis produced different spectra. On the same evening, the aurora was observed by Zollner at Leipzig with one of Browning's miniature spectroscopes, figures 49 and 172, when he obtained the spectrum represented in figure 223. In order to collect sufficient light The slit was opened tolerably wide, and for the purpose of securing an approximate estimate of the position of the lines of the auroras. Those of lithium and sodium were produced simultaneously by means of a spirit lamp. The line in the green part of the spectrum is in all probability the characteristic aurora line 1474K. The red line in this case also was only well seen when the instrument was directed to those parts of the sky which appeared to be deep red, while the green line was brilliant in every part of the aurora. In the blue parts of the spectrum, the faint bands and bands, ASS were only occasionally seen, of which the most striking was the broad dark band SS as it appeared against a bright background. The English observers speak of some remarkably faint, ill-defined bright bands near F and a little beyond it, as well as of a continuous spectrum, BQR between D and F. Zollner, on the contrary, regards these ill-defined bands in the blue as the remains of the continuous spectrum which has been broken up by the darted absorption bands, ASS. It was not till after the disappearance of the aurora that Zollner was able to observe in the same spectroscope the spectra of hydrogen, nitrogen, oxygen, and carbonic acid in Geissler's tubes. Nevertheless, this observer was convinced, in consequence of the simultaneous observation of the spectrum of sodium and that of lithium, that the red line of the aurora was not coincident with the brightest parts in the spectra of any of these four gases. It is more refrangible than the red hydrogen line, H, which is acknowledged also by the English observers, and may possibly, according to Zollner, lie near the position of the group of dark telluric lines, A, angstrom, figure 95, plate 6, situated between C and D in the solar spectrum, the mean wavelength of which is 6,279 of a millimeter. Since the chief lines in the spectrum of the aurora borealis are not found to be coincident with those of any of the spectra hitherto observed of terrestrial elements, Zollner concludes that if the light developed by the aurora be chiefly of an electric character, analogous to the gases made luminous in a vacuum tube, it must belong to a temperature lower than that at which it is possible to observe the spectra of gases rendered luminous in a Geissler's tube. The spectrum of the aurora borealis is not therefore coincident with any of the known spectra of gases of our atmosphere, because it is a spectrum of an order that has not yet been artificially produced. For a further explanation of the mysterious phenomenon of the aurora borealis, more complete measurements of the position of the various lines of its spectrum are necessary, made at various distances from the North Pole, especially within the polar circle, while, on the other hand, physicists will feel impelled to test by suitable experiments the ingenious and well-grounded theory of Zollner and compare the results of their investigations with the spectroscopic observations of the aurora borealis.